based on optimum edge cut C, which achieves h of g, and it separates the graph into two parts, A and B. So for A, for example, if V is in A, we call it that F should be 1 over volume of A. If V is in B, we call it minus 1. So we defined your F like this. I mean, let's write it. Volume of A if V is in A, minus 1 over volume of B if V is in B. I think I have explained this in my playlist in Scalable Machine Learning about spectral clustering, but let's just review it. So, what is lambda 1? I mean, you can write that lambda 1 is just infimum of sum of f of u minus f of v squared divided by f of v squared d of v. And so we have lambda 1. If you just plug in this f here, you will notice that lambda 1 is upper bounded by C, 1 volume of A plus 1 volume of B, and this is less than 2 the cardinality of C, because C, remember, this is the optimum edge cut, and divide by minimum of volume of A and volume of B, and you know this is 2 times your Cheeger constant. And we have proved. So because lambda 1 is now less than equal to 2 hg. So now we have proved one side of the Cheeger inequality. Another side of Cheeger inequality is more important. I call it a theorem. So that for a connected graph G, we can say that lambda 1 is lower bounded by hg2 over 2. And this is the work of Cheeger in his thesis. I mean, his thesis was just proving this, nothing else. And to prove this, I can say that consider your harmonic function f, and that has eigenvalue lambda 1, and we just order the vertices of G according to f. What I mean we relabel the vertices such that f of vi is less than f of vi plus 1 for I between 1 and n minus 1. And without loss of generality, I can say that, let's just say that those vertices, that the sum of them is greater than, over all f of v that are negative, if they are greater than, assume that I pick something like this. Then for any I should be less than the cardinality and greater than 1, we consider the cut Ci to be all of the Vj, Vks, all pairs of your edges, that J is less than I, less than K, less than N. So this I is here. So it separates that. And so it is clear that this minimum of, let's call it alpha, this minimum of Ci over minimum of sigma dj and sigma dj for j greater than I, for j less than I. This it is clear that alpha greater than hg. And we can consider the set V plus of vertices. So V plus, I mean all vertices that are greater than equal to 0. And so the corresponding edges is E plus. So either U or V is in V plus. So all edges that are either U and V is in V star. So we just defined this interesting function. If U is in V plus, it is f of x. If otherwise, it is 0. Just plug that into lambda 1 to make a lower bound. Lambda 1, by definition, you can write f of v, v in v plus. But now we have formed this as like this, f of v minus f of u, and u and v is in edge positive. Divide by f squared of v d of v. V is in v star, v plus, and this is greater than, because we have limited our g. So you see, most of the time it goes to g's is just 0, and so it is lower bounded. So this fraction is lower bounded by g dv, so it can't go down more than this. And here u and v is edge positive, g of u minus g of v squared. Now let's carry on. This is just equal to g of u minus g of v squared. I didn't touch this. I didn't touch denominator. But, and same as usual, u and v is in E plus and v is in v. So I just multiply numerator and denominator by the same factor. G of u plus g of v squared, g of u plus g of v squared, so the same factor. And because this is just 1, and so this is greater than equal to, now you can write the denominator easily at something like this, and all of them squared. And because you can reduce it, because it's some positive number, so you can write this as 2 times g2 of v dv squared. And if you carry on, you will notice that it is sum of I g2 vi minus g2 vi plus 1 ci squared 2 g2 of v dv squared. And this is greater than, here we use telescopic sum because g2 vi minus g2 vi plus 1, I plus 1. And this is times alpha that we defined, and then dj2, j is less than I, over 2, again the same thing, g2 v dv d2. And so this is a telescopic sum, And then if you reduce that, it is less than 1. So everything is greater than alpha 2 over 2, which is greater than h of g over 2, as we observed before. So we have proved the Cheeger lower bound, Cheeger inequality, the lower bound of that. So if you combine the lower bound and upper bound, you will notice that lambda 1 is sandwiched between Cheeger constant squared over 2 and 2 times Cheeger constant. And this is Cheeger inequality that is very popular in both machine learning and graph theory and computer science. And now I just want to say one more theorem, and then we go to random walks on graph and another perspective to spectral graph theory. So for a connected graph G, we can say that your lambda 1 is greater than g of g squared. Remember, g of g is the vertex expansion, not edge expansion, vertex expansion. So you can say everything with your new variable, which is vertex expansion, 2d g of g squared. And your d is the minimum, your d is the maximum degree of your graph. So, and I know I'm completely mesmerized and excited by the work of Cheyenne, James, Luca, amazing people. And but before I talk about their theories, I would like to start with the work of another perspective to spectral graph theory, which is random walks on graph. All of them are completely equivalent, but probabilists only like to work on random walk because they can use measure theory, ergodic theory, probability, and stochastic processes, and those martingale tool, super martingale, sub martingale. What else do we have? Brownian motion. All of those theorems and technology for improvement, for theory developments. And the random walk on graph, people like Yuval Perez. I'm very impressed by this guy, Yuval Perez. Very nice person. He's the advisor of Cheyenne and those great minds. And Ben Morris, of course, Ben Morris, they wrote a paper, Evolving Set Mixing and Heat Kernel Bounds, in 2008. It's a very, very interesting work. Many citations, many people. And he has also, you can also find all of the lectures in YouTube. And Yuval Perez is very active in teaching as well. So he's also a good teacher. We should talk about Markov chain mixing time. But let's start. Let's assume that you are not familiar with these literature. So a distribution is called a distribution pi, and your state is stationary if p pi is p. And what is your transition matrix? The transition matrix of a Markov chain. For example, we have A, we have B, we have C. This is your graph. And for example, from C to B, this is 0.4. From A to C, this is 0.1. From C to A, 0.6 and 0.9, something like this. So your transition matrix is just the probability of transition, as the name suggests. So A, B, C. And the nodes, we call it the states. Of course, it is related to physics as well. And your states could also be generalized to not hypergraph, I mean a set of vertices. For example, an expander. So if we have a set of expanders, it means that we have a set of states. But if we don't talk like that, it means that your state, it means that it is a state, it means that it is in one of your vertices. So going from vertex A to A, there is 0 probability. Going from vertex A to B is 0.9, 0.1. This is the probabilities. The important things is that the sum of these rows should go to 1. Some of them should, but not the column of them. So we start with A, and your start distribution, this is the start distribution, is 1, 0, 0. So after one step that your particle moves, so sigma p is 1, 0, 0 multiplied by this matrix, you get 0, 0.9, 0.1. So this is still not stationary, as you see, because this should be satisfied in order to say that it is stationary. So the probability of reachability is very important, and in future of these theories. Probability of reaching A is the probability of starting at A, and so these are independent events, and reaching A. So 1 multiplied by 0. So the probability of reaching B is probability of starting at A and reaching B. Probability of reaching C is probability of starting at A and reaching C is equal to 1 point, which is 1. So you see how these are related to probability. And by definition, we would say that a Markov chain is irreducible. A Markov chain, M equal to state space omega and transition probability P, is irreducible if there exists a path in the transition graph from every state to another state. Every state to another state should be a path. It means that you don't want a graph that is disconnected. You want to reach from any of these vertices to any other vertices. So it is irreducible. And another definition which is useful is, for example, a Markov chain is aperiodic if for each state S, the GCD of all walks lengths from S to S is 1. So let's talk about some lazy Markov chain. You know how, in order to avoid stacking in one state, we define lazy Markov chain. It means that with probability half, you stay there, you don't go anywhere. With probability half, you move to the another state. And since I love ergodic theory, I should say that a Markov chain M is ergodic. You know, ergodicity is very important in physics and statistical physics, and very important. For example, I remember when I was in Manchester University, I was interested in long time walk of a dynamical system, long time execution of a long time run of a dynamical system. For example, it has many attractors. For example, goes here, and then again goes here. So, for example, here we have two strange attractors. And